Today we will study what is called centrality measures in a social network. So, to motivate the problem of centrality measures, let us see a few interesting cases. So, the first is the problem of information percolation. Think of a friendship network. So, every node is a person and edges represent friends, and this is a symmetric network in the sense that if 1 is friend of 4 as shown in this network, then actually 4 is also a friend of 1. So, this is an undirected network. Now, I ask you this question that in this friendship network of 8 persons, suppose there is some information that suddenly gets known to one of the persons, then what's the probability, or who are the nodes or friends in this network who are most likely to get this information very fast? Put it in another way, let me give you a more concrete example. Suppose that one of your friends suddenly knows that the mid-sem papers, what are the questions in the mid-sem papers in complex networks theory, and he knows it before the exams. So, he will naturally try to, suppose he is benevolent, he wants all the friends to actually gain from his knowledge. So, he will tell all of you, right, he will try to tell all of you, but he does not know all of you, he will first tell his friends and then his friends will tell friends of friends and so on. So, it will spread on the network. So, who are the people in the network who are supposed to get this information, who are more likely to get this information really fast? So, this is the question. Can you guess like what properties a person has which increases his or her likelihood to get this information fast? Okay, so the first thing that I get from you is degree. So, if I am right, what you mean to say is if the degree of a node is high, you assume that that node has a more chance of getting that information faster, which is to some extent true, but is it always true? So, I might have only one friend, but is it always true that I have really low probability of knowing the information fast? Okay. So, the second thing is, even if my degree is low, if I have friends who has high degree, then also it is a very good case. I have a good chance of knowing the information fast. I heard somebody saying something about paths. Can you be more specific?
Distance, the diameter of the network, as in if the network is a small network, then
yeah. So, what Amritayan is telling is if the network is small in the sense that every node is reachable from every other nodes in few steps, then the information will spread over the network very fast, which is true, but the question is like which nodes are more likely to get that information. So yeah, so that node should be actually very close from most of the nodes in the network, which is like the node should be in the center of the network. So, remember the title of today's lecture is centrality. So, there comes the notion of the center. In the center, which means you want to say that it is close to most of the nodes. Okay. Anything else? Let us see. So, we proceed. Okay. So, let us proceed with another example which is very similar actually. So, searching in the web. Here we again have 8 nodes. Actually, the graph structure is very similar except for the thing that now it is directed graph. So, 1, 2, 3 and all these nodes represent some web pages, and these links represent some kind of hyperlinks. So, this page web page 2 has a hyperlink to web page 1 and so on. So, it is the famous hyperlinked structure of the web, if you call so. It is a very small version, a hypothetical version of the same network. Now, if I ask the question which sources do you think will contain very authoritative information which is most likely to be correct. Webs has a lot of material, right, and not all the web pages have the right things written there. So a lot will have junks. So can you like look at this hyperlink structure and guess like which nodes might have more authoritative information? Okay, so for a directed graph, actually this is a different problem. So let me draw a line. So for a directed graph, you say it's high in degree. If a node has high in degree, so can you generalize this second point in this case? So suppose a node doesn't have high in degree, but what if a node which points to it or is pointed by has high in degree? Which case actually holds here? Which of these cases? Got the question? The node may not have high in degree, but still it may be authoritative under what condition? Right. So a node which has high degree is authoritative, but anything to which an authoritative node points to is also authoritative. So it's kind of going recursive. We'll come back to all of them and work out the details, but let's first try to just set the stage with a few questions. The third one is actually spreading of STDs. What do you mean by STDs? Sexually transmitted diseases. So it's a very well studied area actually. So people study the interaction, the sexual interaction network. Here the nodes are again persons, and an edge represent a sexual interaction going between these two persons. Now in this network, again, if I ask the question, who are the persons who are most likely to be affected by some sort of sexually transmitted diseases, like say AIDS, then again you have the same answers, right? It can be degree of the node, which would in this case mean how many sexual partners a particular person has. So higher the degree, higher the chance of getting a sexually transmitted disease. However, on the other hand, a person, like say consider node 3 here, is actually having only one partner. So actually 3 is what is called a faithful person, but unfortunately 2 is actually not a faithful person. 2 has lot of partners. So by the same logic, like friends, if your friend has a high degree, you are in trouble, means you are central to the network. So in this case 3 actually has a high chance of getting AIDS because his or her partner has a high chance of getting AIDS. Okay. So as we have already seen that these are questions from very different domains. One was from web pages, one was from friendship network, one from sexual interaction network, but all has some common answer. And the answer is, in one word, nodes which are most central to the network is actually the node which has the highest chance of getting the information fast, has the highest, in the case of sexual interaction network, has the highest chance of getting sexually transmitted disease. In the case of web pages, it has the highest chance of being an authoritative source. So we have to define some sort of a mathematical notion of centrality about the nodes in the network. And before going to the mathematics of it, let's look at some of the very simple, means a vague definition. So this is a very good vague definition. It helps you to remember what centrality. It says there are 4 P's, and nodes which have all these 4 P's are really central. What are these P's? These are power, prestige, prominence, and importance. I guess this capitalized P in importance is for which what they call it 4 P's. So in case of social network, actually it makes sense. So the nodes which have power, which have prestige and prominence and importance. For web pages or other kinds of networks, you might not exactly use the terms power, prestige or prominence, but definitely you can use analogy of these kind of things. So there are various measures of centrality, as we have already come across 3 actually. I remember you telling me one was the most important and obvious one was degree. If the degree is high, you think that the node is really central. So, it is called degree centrality. The question that here you are answering is how many friends do you have in case of a friendship network. So, degree is simply you know how many immediate friends you have. It is a very simple measure, you can measure it immediately. So, again the measure of centralization of a network, so you know centralized and decentralized, the concepts of centralized and decentralized. So, say a government can be centralized if you know the national government controls everything, it looks after everything. A government is decentralized like in say United States, where every state controls its own you know issues. So, a government can be highly centralized or highly decentralized, it can be somewhere in between. Similarly, we can talk of networks being highly centralized or highly decentralized. So, degree can give you an idea of centralization. Here are two examples. Think of a star network. So, you know how a star network looks like, right. So, suppose there are n nodes in a star network, what will be the degree distribution like? Tell me how many nodes will have what degrees? Right. So, one node will have degree n minus 1 and all the other nodes will have degree 1. So, this is a very centralized network, because the single node sitting in the center kind of can control all the nodes. And on the other hand, think of a line graph. What will be the degree distribution here? 2 nodes having 1 and all the nodes having 2. So, it is a least centralized you know topology. Here any information or anything has to travel through all of them. It is more like a fair network, you know, nobody is privileged in this particular network. In fact, ring is even a better example. In a ring network, every node has a degree 2. So, it is not at all centralized, everyone has the same position. So, can you see one interesting thing between centralization and the degree distribution? So, the line graph or the ring graph which are least centralized, for these graphs the degree distribution, how would it look like if you draw it? There is no variation, it is like a peak, it has a very low variance. And on the other hand, if it is a highly centralized network, the degree distribution would have a high variation. So, exactly. So, thus the variation of degree centrality is sort of a measure of the centralization or decentralization of the network. Suppose I ask this question, that how much centralized is this particular network? So, how do you go about it? Let us see. So, first thing is to compute the degree of all the nodes, right. Let us do a very simple work out a simple example, because you know working out examples always give you the insight which otherwise you would never get. In fact, I would also tell you to take networks and really work out a little bit of them. So, this has degree 1, this is 3, this is 3, this is 3, this has 4, 4, 2, 2. So, what is the variance of this network, the variance of the degrees? How do you measure it? Find the mean. So, the mean would be something like 3, right. So, the mean would be something like 3, let us not compute exactly. And then what do you do? You find the standard deviation. So, basically you take all the nodes, say di is the degree of node I, subtract the mean from it, do a square divided by number of nodes and do a root. So, this gives you the standard deviation sigma. Actually, the variance is you do not do the root. So, basically you get the variance that way. So, this is sort of a very standard way to compute the variance, and now you can ask the questions yourself. I am not going to ask you these questions, but you can try to solve yourself. So, what about scale free networks? So, are these centralized or decentralized network? What about the variance of the degree distribution for scale free networks, or what about other kinds of degree distributions. You can ask these questions yourself and try to see. But let us ask a very slightly different question. So, we have defined centralization as the variance of the degree distribution. The question is, when is centralization a good or bad thing for a given network? Under what condition? Think of, okay, I will give you a more concrete example. Think of a peer-to-peer network, or think of a technological network like routing. There are switches which routes some messages through them. And now the question is centralization good, or under what circumstances centralization is good for such a network, and under what circumstances it is bad? Can you think of that? First tell me, do you want such a network to be centralized or decentralized? Centralized. How it will help you? Okay, so there is already some for and against centralization and decentralization, and actually both of you are right. Both has its problems. So you will study these perhaps in more detail later on when you study attacks on networks. So what happens is centralization has a direct consequence on fault tolerance. So suppose in this routing network 1 or 2 nodes fail. Depending on what nodes fail, it might be good or bad. In a centralized network, if the central nodes fail, the whole network fails actually. So that way it's bad. In decentralized network, if it happens, then it's not that bad. However, for random attacks, centralized networks are good. Suppose the nodes which fail, there is no targeted attack. There is no opponent sitting there to destroy a particular node. So it's a random attack. Then the chances, there will be very few central nodes, right? The chances that it will, suppose a network has a billion nodes, out of which only 10 are central nodes. So 10 by 1 billion is like 10 to the power minus 8, which is a really very small number. So for random attacks, it really makes sense to have a centralized network. However, if it's targeted attack, then decentralized networks are better. So I will not go into more details of this, but as I said, you can think of yourself about more interesting properties of what happens, say for example, in scale-free networks. How centralized are they, and given a degree of centralization in such nodes, you can ask the question that are they good models of, say, routers, or say the internet, other technological networks, and so on. So by the way, what's a scale-free network? Yes, you don't know. So scale-free network is a network whose degree distribution follows power law. So you know what is a power law? Oh, you don't know power law also. Okay, let's see. Right. So you know what is a degree distribution, right? So degree distribution is given by this probability pk that a randomly chosen node has degree k, right? Now it can be any probability distribution. It can be a normal distribution, it can be a beta distribution, an exponential distribution, or whatever. So in some cases it follows actually something like this. Say, so the probability that something has degree k is actually inverse, it's a power of k, but of course it has to be a negative power, because otherwise it will not normalize. You can see it can also be positive power, but usually it's negative power, and it's multiplied by some normalization factor, which is a. So this kind of degree distributions are called power laws. This is a power law because you have k to the power minus beta, and these kind of degree distributions occur very frequently in nature, and these are also called scale free. Okay, so this actually is more or less what we wanted to talk about, degree centrality. Let's move to another kind of centrality, which I call the closeness centrality. Again, you have already answered or found out this definition of closeness centrality. You have already told me that. So it is the sum of the shortest paths to all the nodes from a node, but of course the reciprocal of that. Why do we take this reciprocal? Very simple, right? So, the smaller the sum, the better it is. So, that is why we take the reciprocal. Otherwise, it will not match the definition of centrality in other cases like degree, and we will see some other where higher the value, the more central the node is. So, it is again a very simple definition, and again you can compute the closeness centrality for, say, again we do some experiment, do some computation, very simple ones. Let us try to compute the closeness centrality for node, say, 3. Tell me, so the distance from 3 to 2 is 1, right? This node is 1, and then this node is 2, this node, this node, this node, this one, and this one, right. So, you have, right. So, 16 is the sum of the shortest path from this node to all the other nodes. So, then closeness centrality will be 1 by 16. And do you think it will be higher for 6 or lower for 6? The closeness centrality? The centrality will be higher. The sum of the distances will be lower because it is more centrally located in the sense that it is closer to most of the other nodes. Okay. So, it is again a very simple thing. Again we can ask questions like, what does variance of closeness centrality indicate? And okay, let me make it a more concrete question. So, what would be the variance of closeness centrality for a clique? Why it will be 0? Right. So, every node is connected to other node. So, the closeness centrality for all the nodes will be 1 by n minus 1, right. So, it has n minus 1 neighbors every node, and it is having distance 1 from all the n minus 1 neighbors. Is it clear? So, it will be 1 by n minus 1. So, that is the and since everybody has 1 by n minus 1, so therefore, the variance is 0. So, naturally a clique has the closeness variance of closeness centrality 0. What about the degree centrality variance for the clique? Every node has degree n minus 1, that is also 0. So, you see there is a relationship between all the centrality measures. It is not that usually one measure is much better than the other measure, but these measures makes more sense in particular contexts when we try to answer some particular things. Now, what about a tree? What would be the closeness centrality for a tree, say of height n, and what would be the variance? So, here also you can work it out in detail. So, the distance of a node from the root of the tree is all the same, means it depends on the depth. For all other nodes you have to go up and then come down. So, all these distances are actually bounded, but they vary a lot. So, the variance will be in this case high, and this is because tree, as you can see, is a centralized network, and unlike clique, which is a very decentralized network. And what about a ring? Variance is 0, but what about the value?
Proportional is 1 by 2 plus.
Right. So it will be like proportional to 1 by n square, because 1 by 1 plus 2 plus and so on for all the nodes. Okay. So that like is almost what I had to say about the closeness centrality. And as you have seen, degree centrality and closeness centrality are quite related, especially when it comes to variances. So, if you see a network which has a high variability in the degree, the chances that it will be highly variable in terms of closeness centrality is also high, but not always true. You can find out networks where it does not hold, but that I leave it as an open question. Let me ask you again another question. It is slightly different from what I had asked earlier about the sexually transmitted sexual interaction network. Earlier I asked who is most susceptible to get some kind of sexually transmitted diseases. Now I ask this question, who should be removed from this community to kind of improve or rather reduce the chances of spreading of sexually transmitted diseases. So is it the case? So 2 was also the case who is most susceptible to some kind of STDs. So is it the case that somebody who is most susceptible of getting STDs, if you remove that person, the network gets better? That's actually need not be always true. You can think of networks where you can remove the one particular node which is which has a very high chance, has a very high degree, therefore it might have a very high chance of getting an STD, but removing it may not help, because suppose it's a part of a clique, a huge clique, then removing a node from the clique really doesn't help much, because other nodes will be connected and it does not really decrease the susceptibility of the community from spreading of the disease. But there would be some other kind of measures which will tell you that, right. So, let me give you another example. So, think of again a network of friends. So, I do not know most of your names, so I could not label the nodes except for few people whom I knew previously. So, I have put their names here. So, the question is, here there is one node Subroto and here one node Joydeep. This represents Joydeep and this represents Subroto. Now, tell me, is Joydeep in some advantageous position in this social network than Subroto? I will tell you yes, but in what respect? More powerful in what sense? He is connected to 3 different networks. It is not networks, 3 different communities. That is true, he is connected to 3 different communities, but the question is how it helps him. Can you give me a situation where Joydeep is really advantageous?
If anybody has to transfer some message, then it has to go to Joydeep from one community to another.
Okay, I take that. So, Joydeep is an indispensable part. So, if Joydeep says no, I am not going to tell your message to the other people unless you pay me this much money, then everybody will be paying Joydeep and he will get rich soon. So, that is how he can become rich. You can also look at it from a different point, actually the same thing, but slightly different perspective, that Joydeep has information from all the 3 networks and he is now the controller of the information. Suppose he gets some information from this network, it is up to him whether he gives it to this network or not, means this community or not, and he can negotiate, unless you do not pay me, I will not give you the information. So, essentially he can play the role of an information broker in this network, but unfortunately Subroto can't do that. Whatever Subroto knows is also known to many other people and he is not in an advantageous position. So, actually in the case, in the previous question, the case of whom you should remove from the community to make the kind of network less susceptible to spreading of epidemics or other kind of diseases, the answer is also very similar. So, if you remove Joydeep from here, the communities kind of get disconnected. So, there also the communities will disconnect, and whatever, if there is nobody who is HIV positive in this particular community, then that community will remain safe. Even if that community is highly connected, they are they are all unfaithful people, but still they will be safe because they are not connected to the majority of the population. So, this particular measure of centrality actually, which is very important in social network literature. Why? Because it defines social power. It straight away gives you a measure for social power, and this is called betweenness centrality. So, we will go to the mathematics of it. It's again very simple. So, suppose you want to measure the betweenness centrality of the node V. V is here. So, the basic concept is take all pairs of nodes other than V in this network. I have shown you one example, S and T. It could be this and this also, whatever. See how many shortest paths are there between S and T. Tell me how many are there. So, one path, so one path goes like this, right, between S and T. Right. So, you have two. The other one goes like this. Let me draw it in blue. From S you come to this node, then you come to this node, and then directly go here, right. So, there are these two paths. So, if you remove V from the network, actually the shortest path from S and T does not change in the network, because still it will be 3, right. The shortest path does not change because there is another shortest path that I have drawn in red. However, if you keep on removing nodes, eventually the shortest path will start increasing. Suppose in the next iteration you remove this particular node, then the shortest path would no longer be 3, it will be 4 or maybe even infinity, because the graph might get disconnected. So, removing V has an immediate or futuristic an eventual effect on the shortest path distribution of this network. So, we want to quantify this effect. The higher the effect, the higher the betweenness centrality of the node. So, here between means it lies between the path of two other nodes in the network. So, what you are basically doing, if you look at this mathematical definition, you are counting the number of shortest paths between S and T. So, here it is 2. So, basically this part will be 2, and then you are counting how many of them passes through V. So, here it will be 1, right. So, it gets a score of 1/2 for this pair S and T, but then you do all the other pairs. So, then you sum it over. So, you do it for say these two nodes. So, suppose how many, what will be this value for this as S and say this as T? Y1, how many of them passes through V? How many shortest paths? None, right. So, it will be 0. So, it will be 0. So, for many pairs it will be 0, for many pairs it will be half, for some pair it might be even 1. So, let me see. Yeah. So, what about S and this as T? This is 1, right. There is only one shortest path which passes through V. So, it is 1/1, which is 1. So, you compute for all pairs and sum it over all pairs, and the value that you get is what is the betweenness centrality of this particular node V. So, in this way you can compute the betweenness centrality for every node. You only take the shortest paths, you do not take the longest means longer paths. So, what it essentially means is, if you remove that person from the network, the chances is that the diameter of the network will increase. The network, or even if the diameter does not increase, the information flow might take more time in a stochastic sense, in a statistical sense, because it is not the case, right, always, as we will see soon. So, it is not the case always that when you have an information you tell it to all of your friends. It is more a probabilistic thing. You can tell some of your friends, not tell some others. So more the friends you have, higher the probability that you will tell them, but if you don't have any friend, you can't tell anybody. But all this is a stochastic process. It's not that, you know, it's a deterministic process. So it just gives an idea, a measure of the fact that if you remove this particular node from the network, what are the chances that the network, the diameter of the network increases, or the information flow takes more time on the network. So a node with a very high betweenness centrality, actually if you go to this, you know, previous case, you will see that actually this node has a very high betweenness centrality. Why? Because if you want to calculate the shortest path between any node here with any node here or here, that shortest path has to pass through this particular node. So naturally for all those nodes it gets a count of 1. So it has a very high betweenness centrality, and therefore it has a very advantageous position. So in social network literature, such nodes which has very high betweenness centrality are also called structural holes. So for details of what are structural holes, I, you know, kind of encourage you to go and look into the literature. You will find it in any book and a lot of other references. You just see how, you know, it relates to lot of social power and other kind of things. Now a very simple thing here is, means a very simple extension of this definition is, here we have been measuring the kind of centrality for the particular node. So here we were measuring betweenness centrality for a node. Earlier we measured centralities also for nodes. We had centrality, the degree centrality, which was also measured for nodes, and we have reason to measure centralities for nodes, because nodes are actually kind of actors or agents in the social network. They play the most important role. However, you can also extend this idea of betweenness centrality to edges. Isn't it very straightforward? So you count how many shortest paths pass through this edge, has to contain this edge, and the rest of the formula just follows, right? So you take every pair of nodes and count how many shortest paths between them pass through this particular edge, and that gives you the betweenness centrality of the edges. And why this betweenness centrality of the edge is also important? Because it shows you which relationships in the network are really very important. So you might not remove a person from the network. So again, coming to the previous example, actually, suppose you want to disrupt these communities. So if you want to disrupt the communication between this community, one way to do it is throw away Joydeep, say like kill him or do whatever you want, but let him not be a part of this network. This is one way to do it. The other way to do it is, rather than throwing away Joydeep, you might just, you know, snatch this particular tie. You might insist that, you know, he doesn't have any kind of friendship or information with this particular person. So you are removing the edge, because actually this edge has a very high betweenness centrality. So you can also remove edges rather than removing nodes. Yes?
We need to consider all pairs, or are there better algorithms for calculating the segment?
The definition, the question is, do we need to consider all pairs of nodes while we compute this? The answer is yes, as far as the definition is concerned. But then I think your concern is this. So to compute all shortest paths between a pair of nodes will take some order g plus v plus e, and you do it for all pairs. There are n square, so it n square, or rather v square if we have v plus e. So it takes order v cube, and v cube for one node, and you do it for all nodes, it takes v to the power 4. So it's a very expensive algorithm. However, you need not do it like that, right? You can very easily do some dynamic programming. So when you compute shortest path between, say, this node and this node, you already know the shortest path between this and this. So if you do a BFS kind of thing, so and store your results and reuse your results. So there are much faster algorithms which computes betweenness centrality much less than n power 4. You can just go and look at it. I think Newman has given one such very fast algorithm, but there are many. Okay. So, again let us come to a few questions about this time about betweenness centrality. So, think of can you tell me, give examples of networks where nodes have very small betweenness centrality? All the nodes have very small betweenness centrality. It's very simple, right? Right. So, in Click every node has a betweenness centrality of 0 because every pair is connected. So, no shortest path passes through a particular node. And can you think of a network where at least one or maybe some of the nodes have very high betweenness centrality? Star. Again in star what happens is the central node, what is the betweenness centrality of the hub or the central node in the star? It has to be 1, right? All the shortest path passes through this node, but you add this one how many times? Actually n minus 1 into n minus 2 by 2, because there are n minus 1 choose 2 pairs of nodes. Yeah. So, in the ring network if you remove a particular node, so actually what happens in a ring network is, so let us see. So, this is a ring network. Now, in this network suppose I want to measure the betweenness centrality of this node. The shortest path between, so this is 1, 2, 3, 4, 5, between 1 and 2 passes through V. So, it is like 1. What about, sorry, 1 and 5 passes through V. What about 1 and 4? It is actually half, because there are 2 paths, one is this way and one passes through it, and 1 and 3 actually 0, 1 and 2 0. So, you can do it for all the nodes and you will see that it is really not very high for any of the nodes for a ring. And what is the, so can you also compute the betweenness centrality of the nodes in a complete bipartite network? So, first of all, what is a complete bipartite network? You know? So, if there are m in one partition and n in another partition, how many edges? Mn edges. So, what would be the betweenness centrality of the nodes in such a network? Say both sides have n, both the partitions have n. Both the partitions have n, suppose it is easy to make the case easy, it is n and n. So, what happens in this case is only when the 2 nodes are from the same partition, you need to kind of think. If n is greater than 1 and you have partition 1 and partition 2, you are considering a node in partition 1, you are trying to find the betweenness centrality of a node in the partition 1, and suppose you are looking at the shortest path between 2 nodes in partition 2, does it get affected? It is very minimally, because there are a large number of, there are actually n shortest paths and it will be affected 1 by n. However, if you consider 2 nodes in the same partition, it might get affected, but again very minimally. So, like click, this node, this particular network also has less, very small amount of betweenness centrality for all the nodes. So, it is also a highly sort of centralized network. So, now we have seen 3 measures. One is called closeness centrality, one is degree centrality, one is betweenness centrality, and all of them have some interesting properties. We have at least evaluated them for some of these measures, indices for clicks, rings, paths, sometime we have talked about trees, bipartite networks and so on, but they all predict very similar kind of values for all of them. So, the variance is same. Clique always have very low variance because clique is a very uniform looking thing, star has a very high variance and so on. So, all these centrality measures again I am telling you are related, but which one you use depend more on the context. So, therefore, we will go to another very interesting and slightly different actually centrality measure, which you have already given some hint to as the answer to the first question. So, the question is this: suppose you are searching the web, again the initial question, that question number 2, and you have the hyperlinked network of web pages. So, every node is a web page and links are the hyperlinks. I ask you which are the pages which are most popular or which are the pages which are most authoritative. So, tell me if degree is useful, degree centrality. So, here you have two kinds of degree centrality, right? One is in degree centrality, the other is out degree centrality. So, will that be of any use? Which one will be of any use, if at all? Right. So, in degree centrality will be or might be of some use, right? A page having high in degree might tell you that this page is an authoritative source, this page is important. But it may not tell you all the authoritative sources. As we have already seen, a page may have low degree, but still somebody might an authoritative source might point to it. Will closeness centrality help you in any way? Doesn't seem how it can help you obviously, right? Although there might be some relations, but intuitively you don't see any relationship between closeness centrality and this popularity of pages. Okay. And betweenness centrality, what about that? It helps. How it helps? No, you see, these are not this is not internet where each node acts as a router or something. This is a network of web pages. So, it is like a link might mean many things. Basically, there is a hyperlink in page 2 that points to page 1, but what kind of link? Like it can be a related material, it can be an ad, it can be some orthogonal reference, or it can be just cool links, whatever. So, you really do not know what kind of link it is. So, it seems also that betweenness centrality may not help us in obvious ways, right, for this network. So, now the question is, we know degree centrality helps, but only to some extent. Betweenness centrality does not help, closeness centrality does not help at all. So, then what can we do? And how can we improve degree centrality? You look at the degrees of neighbors also.
And based on that,
Assign weights to whom? Assign weights to edges. Please be louder.
Connectivity of the nodes can be some connections are not there. If we establish some connectivity, then it can be useful.
So we define in degree as the summation of popularity of all the neighboring nodes.
So, what he is suggesting is for every node you define something called a popularity, and you redefine the popularity as the popularity of all the nodes which point to it. That might work, but what is the first set of popularities then? How do you arrive at that? Isn't it a problem?
Seed the network with random numbers.
Random numbers, and if you start with some set of random numbers as your seed, then do you know you end up with the same set of kind of popularities at the end? Suppose I start with giving all the nodes the same weight in the beginning and do the computation he is suggesting, and we end up in some particular network with some set of popularities. And on the other hand, suppose we start with, say, giving all these nodes, say, values 1 and all these nodes, say, values 0. So, do we end up, is there any guarantee that we end up in the same set of final values?
Or assign uniform weights and iterate and say stop at some point.
Stop at some point.
After you have explored enough, you won't like to go on.
And what should be the point at which we stop iteration? It's just you are suggesting that we do a fixed number of iterations. So what he is telling is assign weights, assign same weights to all of them, and then iterate for, say, 50 iterations, and whatever you end up with, stop there. So this sounds like a unique way of defining. Depending, given any network, since he has put so many constraints, it will uniquely define ultimately some popularity for each of the nodes. But does it have any mathematical basis, or the question is why we should start with uniform and rather not something else? Or you start with weights which are based on degrees.
Then we can add some more if it is connected to a more popular node.
Yeah, but that's the point. If it's connected to a more popular node, then it gets more popularity. But the point is, at the first place, how do you know which are the more popular nodes?
So based on degree.
Based on degree. So his suggestion is, in the beginning, assign a popularity of degree, which is equal to the degree to all the nodes, and then iterate. And how many iterations you do?
Pick any random number. Maximum degree in the
Sir,
Yes.
why exactly are you trying to assign the weights?
I am not trying, only you suggested me. Some of your friends suggested that, oh, the ultimate aim is you want to find out from this link structure which pages are the most important ones. Okay. So if I give you this network and ask you this question, that all these pages, say, talk of a particular query, say complex networks. You typed a query complex networks, and all these 8 pages have these word complex networks used somewhere or other. But internet has a lot of junk material, right? You really don't know which of these are really useful pages. So the question is, can you exploit this link structure, the hyperlink structure, to find out that which are most likely to be non-junk pages, useful pages? So alternatively, you can think of which are the popular pages, because which most of the people refer to ought to be useful. It's sort of an intuition, and usually it works. But the question is, then you can just say that 6 seems to be a very authoritative page because a lot of things refer to it. But on the other hand, this is just in degree centrality, but in degree centrality won't help you always, because think of the page 7. If you say that 6 is authoritative source, then whatever 6 links to should be authoritative, because 6 should not link to any junk page. So then 7 should be authoritative, 8 should be authoritative, but then in degree centrality doesn't capture. So the question is, can we refine in some manner our definition of centrality so that it captures that even 8 and 7 are popular pages? And to that, your friend suggested start with some initial assignment of popularity and say that one node gets popularity which is equal to the sum of the popularities of all the nodes pointing to it. Keep on iterating, stop at some point. Now there are so many questions coming up, we already discussed. So rest of it, so think about it, and we will discuss in the next lecture.